All right, everyone, I'm going to be talking about Lab 7 or the ideal gas law, or rather, like reviewing it. So this lab is, there's like not a lot to review. So, like, the ideal gas law is just PV equals nRT, where pressure, or P is pressure, V is volume, and P is measured in pascals, V is measured in meters cubed, N is the number of moles, R is a constant, and then T is the temperature measured in Kelvin. All right, so the lab introduction just like introduces you or introduces to you what an ideal gas is. So the two main parts of it are that the atoms do not interact with each other, and the atoms themselves occupy zero volume. So the gas itself can still occupy a volume together, but we're going to model each individual gas particle as having zero volume. Right, so this is like they mentioned that it's an idealized hypothetical model, but for systems that are under certain conditions that I'll talk more about later, it's actually a very good approximation. All right, and so really quickly, I want to talk about what like the pressure in a gas actually comes from. So gases are really a bunch of particles moving around in different directions randomly. And so if you have a wall here and you imagine that I have a gas particle here and it gets thrown into the wall is going to deflect the gas particle to bounce off, okay? And to deflect the gas particle, you have to change its momentum. And if you change its momentum, you're applying a force. And Newton's third law says that if you apply a force to the gas particle, then the gas particle also applied a force to you, which means that the gas particle pushed on the wall, applying a force, all right? And pressure is simply force over area. So if we have a bunch of forces from a bunch of gas particles hitting the wall over the entire area of the wall, then we'll have a pressure. And so that's where the pressure comes from in an ideal gas. All right. And so again, they mentioned that PV equals nRT. All right. And so P is pressure, V is volume in meters cubed, N is moles, R is a constant that's equal to 8.31 joules per mole Kelvin, and then T is the temperature measured in Kelvin. So one thing to be careful with is this V. Like if V equals 1 liter, that doesn't mean that you put 1 liter here. You have to convert this to 10 to the negative 3 meters cubed. All right. And so just make sure you are conscious of that. And what this also means is that like 1 meters cubed is 1,000 liters. All right. And so actually in this paragraph, they talk about something that's pretty important. So like we know that like Ke equals 1/2 mv squared. This is like the kinetic energy, right? And so if you increase the temperature of a molecule, you increase its kinetic energy. And obviously the mass is going to stay the same, so that means you increase the velocity. So when you increase the temperature of a gas, you're increasing the velocity of the gas particles moving inside of it. All right. And then the lab went through and it had you do the actual experiment where you measured with 60 mils and then 50 mils of like initial volume. But really quickly, I wanted to talk about like questions 1 through 3 here. So question 1 is like, did the initial and final number of moles agree with one another for just like either the single 50 mil or the single 60 mil experiment, like not between them. And then theoretically, the initial and final number of moles should agree with one another, because even though you compress, like if you have a plunger and then if you push this plunger down to like compress the gas particles in here, but before they maybe were like more spread out, then you're increasing the pressure, but the number of moles should still stay the same theoretically, right? And so Q2 is like whether the values agreed with an experimental uncertainty. That's like more of a lab thing, like they either did or they didn't. And then Q3 is did the number of moles increase by the amount you expected with this new initial volume compared to the old initial volume. So like theoretically, you should find with like 50 mils, you get like you calculate approximately 0.002 moles of gas, right? And so if we increase to 60 milliliters, we expect this to increase by 60 milliliters over 50 milliliters, which is 6 over 5, which correlates to a 20% increase. So we would expect that our n is now proportional to 0.0024 moles. And so I just wanted to quickly mention that that's how you would find like the expected number of moles. And then in part 2 of the lab, you did another experiment, and you checked if the mole value that you calculated in this experiment matched with what you got initially of like 0.002 moles in the first part of the lab. Theoretically, they should match, but something went wrong in the experiment, they might not. And then Q5 is again talking about whether the amount increased by what you expected. So we expect a 20% increase. And then the summary is like the first question is, why is the ideal gas law an important relation? It's an important relation because we can approximate a lot of gases as being ideal gases. And if we can approximate a gas as being an ideal gas, then we can write the equation of state, which is PV equals nRT. If you write an expression relating P to like V and R and T, then it's called an equation of state in physics. And so if we can write our equation of state, then we can relate these different values and see what would happen in a gas if we change these values, if we can approximate it as ideal. And then the next thing is, what is an ideal gas? So an ideal gas, again, in the beginning, we said it follows two things. There's no interaction. And so like sometimes you'll see that people say an ideal gas has like the molecules can hit each other as long as it's perfectly elastic, meaning no energy is lost. And yeah, that's true. But a lot of times we just say that it's just no interaction in general. But either way, it's the same thing. Doesn't really matter. So there's that too. And then the second thing is just that molecules have no volume. And so this is not the whole entire gas itself. This is the individual molecules that have no volume. Okay, so that's when ideal gas is. And then when is the gas law valid? So it's valid when we are at low pressure or I guess or high temperature. All right. And the reason for that is that when you have low pressure, the gas particles are like really far apart on average. And if they're really far apart on average, which I think is called the mean free path, but don't quote me on that. So if they're really far apart on average, then they're not going to interact. And so like, again, we said ideal gases have no interaction, but obviously real gas particles do interact with each other. So we can only say that they have no interaction essentially if they interact very rarely, which happens when they're far apart from each other. And then or high temperature, if they're moving really fast past each other, then they don't have enough time to really interact. And then it's invalid when the reverse is true. So if we have high pressure, they're close to each other. And if they're close to each other, then they can interact more. Or low temperature. So if they're low temperature, that means that the particles are moving slowly. Remember, because we said that 1/2 mv squared relates the kinetic energy of a gas molecule, and increasing the temperature increases the velocity, and therefore decreasing the temperature will decrease the velocity as well, because the energy is increasing and decreasing respectively in those two cases or those two situations. So if the gas particles are moving slowly, then as they move past each other, they have a lot of time to interact, and that makes the gas not ideal anymore. And then the last question is about the importance of the universal gas constant, which is R. So remember that R is 8.31 joules per mole times Kelvin. And so all this says is that it's like the amount of energy that a gas or that an atom would gain, or like that a mole of gas would gain if you increase its temperature by 1 Kelvin. So I'll say it again. So if you take a mole of gas and you increase its temperature by 1 Kelvin, it will gain 8.31 joules. All right? And so really it's important because it just tells us how energy relates to the temperature of a gas and how much of a gas there is. Then it also shows up in other things, like if you've ever heard of like Gibbs free energy, I think it's negative RT ln of something. But so Gibbs free energy is obviously like one example. It tells you like sort of how spontaneous a how spontaneous a what's the word? How spontaneous a reaction would be. Oh, it's actually ln of k, where like k is like some equilibrium constant. So like you don't need to know this for this class. Like don't worry about it. I'm just showing that it shows up in other things relating to energy. But that's really it for this lab. Thank you.